Right. Okay, good morning, everyone. Okay, so here are some sample problems. Okay, these are the problems I used in the past. Okay, so I'm just showing you some difficulty of the problems. Okay, so something like this will be given in the exam. So, and for the first problem was true false problem, and I'm just asking the answer only. So in that case, you can just mark T or F depending on your belief or knowledge or choice. So depending on your choice, you get 2 points or zero. Okay. So for example, if I consider this mapping T from P3 to P2 and defined by this, and S is given and W is also given here. And then my claim is there exists a subset H of U such that this spans the P3 space. So if you believe it is true, you can mark it true. T true. If you believe it is a force, you can mark force or F. Okay? Something like this. Or in B, suppose that I have three vector spaces, the V, W, and Z, and T and U are defined to be linear. And if I know that the composite of U and T is 1 to 1, then is T 1 to 1 as well? So if you think it is correct, you can mark a T. Okay, so something like this will be given. And or I may ask you some question like this. So S1 is defined and V is defined here, and S2 is a subset of a V, and you can just provide any example of S2 such that this is satisfied. So, okay, so you can just, many students may have different answers, right? So you can have your own answer, and if your answer satisfies this statement, then you get the full credit. Okay. Of course, if you just write down, okay. So, and number two, I'm just asking the answer only. Okay. And number five, I have the following problem. So I gave two bases, beta and beta prime for P2 space. And I'm asking to find the change of coordinate matrix from beta prime to beta coordinate. So for this problem, I'm asking to provide each step to derive the answer. So if you have such a problem, then you need to write down all the steps in detail. Okay? So depending on the problems, of you can just mark a true or false. You can just answer the you can just write down the answer only, or sometimes as in number five, you need to write down the answer or proof with some supporting statements. And if I ask some supporting statements as in number 5, then there will be some partial credits. For the others, there won't be any partial credit. You get the full credit or nothing. So these are some types of the problems for the midterm. I mean, this may be changed, all of a sudden I may give you the, say, multiple choice problem, right? So everything can be changed, but the difficulty will be something like this. So you need to check, you need to see the difficulty of these problems. And for this problem, I expected you would spend about 10 minutes for each problem because some problem has some sub problems. So I gave 6 problem sets for the midterm in the past for this one. But depending on the difficulty, okay, if I give you, say, more simple ones, then you will have more problems. If I give you more challenging problems, then the number will be decreased. So these are some sample types or difficulties of the problems in the exam. And yeah, and I do not provide any solution sets. Okay. So if we have any, so please do not ask me this answer or solution for these problems. You need to check, or you can chat with your classmates if you want, but I do not provide the solution sets. Okay, anyway, that's the information for the midterm, and as I said, we have the exam in a week. So it is not in a week, but we have the exam on 21st, right? So we have the exam on Tuesday. So so please be prepared. And then let's go to, and as I said, the exam covers up to chapter 2. Okay, not chapter 3 is not included, even though I'm considering the chapter 3 today, okay, but that will be covered in the final exam. Okay, let me go back to the definition and then explain this again. So first, given any matrix, given any m by m matrix A, following 3 operations will be called elementary operations. We can perform those operations on certain row or certain column, and these row operations will be called elementary row operations. Actually, in the textbook, and if you see the exercise, there are some examples of elementary column operations, but in most cases, we will focus on elementary row operations. And okay, elementary row operation consists of 3 types. Type 1, you interchange 2 rows of a matrix. And type 2, you multiply a non-zero value to a certain row or column. That is called elementary row operation or column operation. And you multiply some number to a row and then add it to another row, or you multiply certain number to a column and then add it to another column. That is called replacement or type 3 operation. Okay, so and even though I will focus on row operations, sometimes I will introduce the examples of column operations. Okay, so I will consider both row operation and column operation, but as I said, mostly I will focus on the elementary row operations. Anyway, so these are some row operations, and as I said, these operations are reversible. Meaning, if you perform certain row operation to a certain matrix A to get matrix B, then you can go back to A by performing certain row operation. If you perform certain column operation to A to get B, then from B you can get A by performing certain column operation. Okay. And so here, given A matrix, if I interchange first the two rows, I get B matrix. Or if I multiply 3 to the second column of A, you get C matrix. So these are the results of elementary row operation or column operation. Now, one very important theorem we just considered the last day was this. Okay, and in this theorem we are considering the matrix by elementary matrix. So what is an elementary matrix? Elementary matrix is a matrix obtained from the identity matrix by performing a single elementary row operation. So given this I, by if I perform the type 1 row operation, you get E matrix. If I consider the scaling operation, I mean the type 2 row operation, you get F. I mean, F can be obtained from the elementary column operation of type 2 as well. And G is obtained from the identity matrix by performing the type 3 operation. Now, then what is the usage of this elementary matrix? One of the usages of the elementary matrix is theorem 3.1. 3.1 says, given A matrix, if you perform elementary row operation on A and the resulting matrix is the matrix B, then when you perform the same elementary row operation on identity matrix to get a corresponding elementary matrix E, then B B matrix will be the same as E times A. Let me go back to this example here. M is, okay, this one. B is obtained from A by interchanging the first row with the second row, right? So if I perform the same row operation on the identity matrix, given the identity matrix with 1 0 0 0 1 0 0 0 1, when I interchange first the two rows, you get an elementary matrix of 0 1 0 1 0 0 0 0 1. Now, given this E matrix, if I pre-multiply A matrix, so if I multiply 0 1 0 1 0 0 0 0 1 times A matrix, 1 2 3 4 2 1 negative 1 3 4 0 1 2. Then when I multiply this 0 1 0 with the first column of A matrix, then you have only 1 1 in the second entry. So only second entry of this first column will survive. So you get 2. And when you multiply this 0 1 0 to the second column of A, you get 1, then negative 1 and 3. And when you multiply 1 0 0 with 1 2 4, then you get 1, then 2, then 3, then 4, and so on. So when you multiply E with A, you get B matrix. Now, given the identity matrix, 4 by 4 identity matrix, I obtain 630 in the second column of C by multiplying 3 to the second column of A matrix, right? So if I perform the same scaling operation on 4 by 4 identity matrix, so here, in case of the column matrix, you need to post multiply the elementary matrix. So identity is now 4 by 4 matrix. And then if I multiply 3 to the second column, then the corresponding matrix will be 1 0 0 0 0 2 0 0 0. Okay, so 3 is multiplied. 0 0 1 0 0 0 0 1. Now if I post multiply E to A, so given A, if I multiply 1 0 0 0 0 3 0 0 0 0 1 0 0 0 0 1, then when you multiply these two, okay, you get C matrix. Okay, so so given A, any m by m matrix, if suppose that B is obtained from A by performing certain elementary row operation, then you perform the same elementary row operation on an m by m matrix. So in case of row operation, the size of the identity matches the number of rows. So if A is on m by n matrix, then you consider an m by m identity matrix, and then you perform the same row operation, okay, on I identity, and then you pre-multiply the resulting matrix. Pre-multiply the resulting elementary matrix to A, then you get B matrix. If you've performed a column operation, then you need to consider the n by n identity matrix. You perform the same column operation on this identity matrix, and then post multiply that E with A. So A times E is computed. So that will be, okay. So in fact, E is obtained, yeah. And conversely, if E is on elementary m by m matrix, if E is on elementary matrix, then EA, if you pre-multiply this elementary matrix, then you obtain a matrix by from A by performing the same elementary row operation as that which produced E from the identity matrix. So you can read the proof in the textbook, or but more important part is just understand this concept. So please try some examples. Okay. So here is another example. So suppose that, yeah, as I said, this was already considered. So in from A, we obtain B by interchanging two rows. So if I perform the same operation on the identity matrix, you get this elementary matrix E. So if you multiply E to A, you get B matrix. Now, as I said, elementary row operation is reversible. That means elementary matrices are invertible, and the inverse of an elementary matrix is on elementary matrix of the same type. Please note that the previous example, given the identity matrix, if I consider type 1 elementary row operation to get E, which is 0, 1, 0, 1, 0, 0, 0, 0, 1, then multiplication by E will interchange first the two rows, right? So given E, if I pre-multiply E, then this E will interchange first the two rows of the E following, then you get the original status, the identity matrix. So the inverse of E will be E. So in other words, if you perform the interchange operation, I mean type 1 elementary row operation, then the inverse of that elementary matrix will be the elementary matrix itself. And what if I consider the scaling operation? So if I consider, say, 1 0 0 0 3 0 0 0 1. So if that will multiply 3 to the second row entries in A matrix. Okay? So whatever follows, so whatever follows, you multiply 3 to the second row of the matrix. So mm, mm. So this will be the identity matrix because this one will scale the second row by a factor of 3. So 1/3 multiplied by 3 will become 1. So you get the identity matrix. So this is the inverse of F, and here is F. Okay. And and if I consider the type 3 operation, so if I consider the replacement, G, so for example, if I multiply 2 to the first row and then add it to the third row, what do I get? Then first the two rows are not changed, but if you multiply 2 to the first row, you get 2 0 0, and then if you add it to the third row, you get 2 0 1. So you multiply 2 to the first row and then add it to the third row. So if I multiply G with 1 0 0 0 1 0 negative 2 0 1, then you get the identity matrix. So the inverse of E is E. Inverse, but so in case of the type 1 interchange operation, the inverse will be itself. And in case of F and G, if you consider the scaling or replacement, the type of the elementary operation will be the same, but in case of F, you need to consider the reciprocal. In case of G, you need to consider the additive, you need to put negative sign. So these are, okay, so elementary matrices are invertible. The inverse of an elementary matrix is an elementary matrix of the same type. And here are some examples. Now, in case of the identity matrix, I have 1 0 0 0 1 0 0 0 1. In case of E, in case of E, I have this one and this one. So actually, in case of the identity matrix, I had one only on the main diagonal, and all the off diagonal entries were zeros. But in case of the interchange, yeah, in case of the interchange, the corresponding elementary matrix will have this shape. In case of F, you have zeros. All the off diagonal entries are zeros, right? All the off In case of F, the all the off diagonal entries are zeros, and along the main diagonal, you have ones except one value. Okay? In case of G, you have one non-zero value in the off diagonal region. So that is the only difference between G and the identity matrix. Okay, so you can check the problem number one, and actually let us look at the problem number two. Suppose that I have these three matrices A, B, and C, and find an elementary matrix that transform A into B. Now, how do I obtain B from A? What's the difference between A and B? The first columns are the same, the third columns are the same, but only the second columns are different. Okay. Now, how do I obtain this 0, -2, -3 from this from A? You can perform replacement operation, right? So if you multiply -2 to the first column, you get -2, -2, -2. If you add this column with original second column, then you get 0, -2, and -3. Okay. So that means this B matrix can be obtained from A by multiplying 1 0 0 negative 0 -2 0 0 0 1. Right? So B can be written as a product of two matrices, A times this matrix, the elementary matrix. So in this way, I could obtain B. Now, then how can I obtain C from B matrix? Now, the first row 1 0 3 are the same. And the third row 1 minus the 3 1 are the same. Okay? But only the second rows are different. So I need 0, -2, and -2. So how do I obtain this triple from 1, -2, and 1? You can perform elementary row operation on B matrix. So if I multiply -1 to the first row, you get -1, 0, -3. And then if I add that row with the second row, you get 0, -2, and -2. Okay. So if I do this, then C can be obtained from B matrix by pre-multiplying 1 0 0 -1 1 0 0 0 1. Then you get C matrix. Right? And if you so so I could transform A to B and then B to C. Now you can repeat such procedures, and you can transform C to identity matrix. right? You can check this. Okay. Then why do I consider this? Okay, so here's what I did. Given A, I obtain B by performing certain column operation. Okay. So B is obtained from A by multiplying certain elementary matrix. Say E1. Let me call this guy as E1. Then C is obtained from B matrix by performing certain row operation. So if I consider certain elementary matrix, then when I pre-multiply that matrix to B, you obtain C matrix. And E2, B is A times E1. So given A, when I multiply some elementary matrices, you obtain C matrix. So I could write down C or even B can be written as a product of certain matrices, and in that product, one of them is A matrix. Okay? So please remember this fact, and then I will return to this. Okay, now let us consider the next section, rank of a matrix. And okay, what is the rank of a linear transformation? How do we define the rank of a linear transformation given a mapping, given a linear mapping? How do I define its rank? Rank of a linear transformation is counting the number of vectors in a basis for the range. In other words, we need to we need to check the dimension of the range. That is called the rank of a linear mapping. In section 2, we consider the rank of a matrix. So what will be the relation between these two? So here, given m by n matrix A, we define its rank, okay, using the rank of the linear transformation L sub A. So what is L sub A? L sub A is a left multiplication transformation. That means given any vector V in Fn space, if the image is A times V. Mm, we have A times V. Yeah, that is the image of this. Mm, sorry. So A times V is the image of a V under L sub A, and the rank of the linear transformation L sub A is just counting the dimension of the range of this transformation. That is what I mean by the rank of the linear transformation. Okay. And the rank of the matrix is defined by this. Okay. Theorem 3.3. So let's suppose that T is a linear transformation between finite dimensional vector spaces, and beta and gamma are the basis for V and W respectively. Then the theorem says rank of this linear transformation equals the rank of the matrix when representing this t when beta and gamma are ordered bases for this v and w respectively. And this is trivial, so you can easily check this. The 3.4 is interesting. So given m by m matrix, if P and Q are invertible matrices, then rank of A times Q will be the same as rank of A. Okay. Then, okay, first of all, what is the rank of A times A and Q, A times Q? Rank of A times Q, the value on the left is defined by, oh, by the dimension, the by the rank of the linear transformation representing the composite of A and Q, right? So this is defined by dimension of the range of this linear mapping. And left multiplication by A times Q is the same as that is just the composite function. So this is the same as, oh, okay, so the range of left multiplication by A and Q will be the composite of these two. So I can split this composite with these two functions, two mappings, and the range of L sub Q. So what is the domain? Domain is Fn. So the range of this composite will be the range of Fn under Q mapping and then mapping A, matrix A. Now, since Q is assumed to be an invertible matrix, it is an isomorphism, meaning the image of Fn under Q will be just Fn space because this is an isomorphism. Then that means this value is just the image, the range of L sub A. So that means, so the range of this multiplication by A and Q will be the range of L sub A. Then the range of this composite will be the range of L sub A, and that is just the rank. So that means the rank of the composite, I mean the product A times Q, will be the same as rank of A. And this comes from the fact that these P and Q are invertible matrices. So what is the meaning of this? That means if I have an invertible matrix, the multiplication by inverse matrix, the multiplication by an invertible matrix from the right does not alter the rank. So the rank of A times Q is the same as rank of A. And if I perform a similar step, then rank of P times of A will be the same as rank of A. So that means if we multiply an invertible matrix, excuse me. So if you multiply an invertible matrix, then the rank is not changed. In other words, the dimension of the range is not changed. Dimension of the range means the number of independent vectors in that range. So the multiplication by matrix. Okay, so that is representing certain mapping, right? And this mapping does not change the number of independent vectors. So if A is true, then you can easily prove that if prove B, and if A and B are true, then we can derive rank the statement to C. Okay. So most importantly, so I have so if I consider elementary row operation, then so if I obtain B from A by performing some elementary row operation, then rank of B will be the same as rank of A. And if I consider the elementary column operation, then so if C is obtained from A by performing elementary column operation, then C is A times E. And even in that case, rank of C and rank of A will be the same. So elementary row operation or elementary column operations are rank preserving. Rank is not changed. Okay, theorem 3.5 is important. And so let me check this line by line. So theorem 3.5 says the rank of any matrix, so rank of a matrix equals the maximum number of linearly independent columns. In other words, the rank of a matrix is the dimension of the subspace generated by its columns. This is important. Okay, so let us check this. First of all, for any matrix, as I said, rank of a matrix is defined by the rank of the left multiplication operator, and rank of a linear transformation is defined by the dimension of the range corresponding to range of this mapping. So rank of A, rank of L sub A, and dimension of the range of L sub A, they are all equal. Now, suppose that beta is the standard order basis for Fn, and then this beta as a basis for Fn, this spans Fn. So the range of left multiplication by A is span of L sub A of beta, and span of L sub A of beta is defined by span of this set. Okay. Now, but for any j, L sub A times E sub j will be the jth column, right? Will be the jth column of A. I mean, so suppose that A, B, C, D, E, F, G, H, I. Then, yeah, A times E1 will be A, B, C, D, E, F, G, H, I times E1, 1, 0, 0 will be A, D, G. Or, right? I mean, A times identity will be A, right? So A times E1, E2, E3 will be A. That is A1, A2, A3. Okay. So, so A times EJ will be the jth column of A. So L sub A of E1 is the A1, and L sub A of E2 will be E2, and so on. Then rank of A is rank of A equals the dimension of the range of L sub A, and since the range of L sub A is the span of A1 up to AN, and so its dimension will be the same as the rank. Okay, so given this A matrix, the first two columns of A are linearly independent because just look at the second row, right? The second entry of the first column is 0, and the second entry of the second column is 1. So no matter what you multiply to the first column, you cannot obtain the second column. In a similar way, when I look at the first row entries, the entries are 1 and 0. So no matter what you multiply to the second column, you cannot obtain the first column. So A1 is not a multiple of A2, and A2 is not a multiple of A1. So first, the two columns are linearly independent, but as you can see, A3 is the third column is A1 plus A2. So only two columns are independent, but the third one is dependent. Then the theorem says the rank of matrix A, for this, you can just count the number of linearly independent columns, which will be 2. So that is the rank of this matrix. In example 2, suppose that I have a, okay. Mm, uh, yeah, let us consider the following. Okay, in example 2, suppose that we have this matrix A, and if I subtract the first row of A from rows 2 and 3, so I'm just performing replacement 2 times, then the result is this. If we now subtract twice the first column from the second and subtract the first column from the third, then you get this. Then, so if I perform such operations, then the third column can be written as a linear combination of the first two columns. right? So this third column can be written as a linear combination of first two columns. So the rank is 2. So the rank is 2. So before we go to the next part, so let me summarize. So given T, okay, what is the rank of T? That is representing dimension of the range. Okay. So that is the general definition. That's the definition in general for the rank of a mapping. But how about the matrix? You can consider this one as well. Yes, that is fine. But since we are considering the determinants of the rank of a matrix, the easier way is to count the number of independent columns in A. Okay. Of course, you can later we will see that you can count even the independent rows in A, okay? Even though the textbook says this rank will be the same as the number of independent columns. Now you can count if you want. If you have that information, you may count the number of independent rows if you want. Okay, so that will be also the rank. But people usually consider the independent count the number of independent columns because it is easier than counting the number of rows. But anyway, the number of independent rows and the number of independent columns will be the same for any matrix. Suppose that A is an m by m matrix with rank R. Okay. Oh, one more thing. One more thing. So the rank of A is the number of independent columns or rows. So for an m by n matrix A, the rank of A will cannot be greater than the number of columns, right? Because if your matrix has n columns, then you have at most n independent columns. So the rank cannot be greater than n, or it cannot be greater than m as well. So rank of A will be bounded by the minimum of m n. Okay? So the rank cannot be greater than the number of columns or the number of rows. Okay. Mm, Now, suppose that A is an m by m matrix, and suppose that I know that there are only R number of independent columns, so that the rank is R. Then, as I said, this R cannot be greater than the number of rows or columns, first of all. And if I perform some elementary row operations or column operations, then this matrix can be transformed to this shape, where I sub r is a matrix with ones along the main diagonal and zeros everywhere else. So this is your I sub r matrix. And for all the others, they are just matrices. Okay, so O1, O2, O3 are just the zero matrices. And I sub r is the identity matrix. Okay. And please note that I have the identity matrix with R ones. Okay, I sub R. So for example, if I have a matrix, okay, now how can I obtain D from a matrix? How can I obtain a D from A? Well, if I have D, then definitely, okay. So I'm just, so D is a matrix with this identity on in the upper left corner, and it has only 3 ones. So that means the rank of, so that means rank of D is 3, and that also confirms that rank of A is 3 as well. Then the question, going back to my original question, how can I derive D from A matrix? So we first start with the first row, first column entry. Okay. If you have a non-zero value, okay, then that is fine. But if you have 0, okay, then you need to perform an interchange operation with the first row. You can choose any other row as long as in that column, if you have non-zero value, you can choose any row. So for example, if I consider the second row and then if I interchange these two, what do I get? 4, 4, 4, 8, 0, 0, 2, 4, 2, 0, oops, 2, 0, 2, 4, 2, 2, and 8, 2, 0, 10, 2, 6, 3, 2, 9, 1. If I divide the first row by 4, or in other words, if you multiply a quarter to this first row, and yeah, the 1/2 to the second row and 1/2 to the third row, what do I get? 1, 1, 1, 2, 0, 0, 1, 2, 1, 1, and 4, 1, 0, 5, 1, and then I have 6, 3, 2, 9, 1. And then if I multiply -4, so so please remember that I just considered the first row, first column entry, and then I change it because all the numbers are multiples of 4. I just perform the sum scaling operation to get this 1. Okay, and then given this, I want to multiply -4 to the first row and then add it to the third row. what do I get if I multiply negative 4 to the third row? You get -4, -4, -4, -8, and 0. So if you add them, 1, 1, 1, 2, 0, 0, 1, 2, 1, 1, and 0, -3, -4, -3, and 1, right? And then I have 63291. So what if I multiply -6 to the first row? Then you get -6, -6, -6, -12, and 0. So if I add these numbers to the fourth row, you get 0, -3, -4, -3, and 1. Okay. Now, so when I look at the first column entries, I have 1 and zeros. Okay. Then you go to the second column, but not the first row, but second row, second column entry. That is 1. You have 1. Okay. Then so previously when I considered the first row, first column, I initially had the 0. So I interchange it to get non-zero value, and then perform replacement a few times to get this. Now given this matrix, if I multiply 3 to the first row, you get 0, 3, 6, 3, 3. If I add those numbers to the third row, what do I get? 1, 1, 1, 2, 0, 0, 1, 2, 1, 1 are the same. Now you get 0, 0, 2, 0, 4. And then the same numbers are can be added to the fourth row. Then you get 0, 0, 2, 0, 4. So when I look at the second column, you get 1 and zeros. Now, for a moment, I do not consider the 1 above this. I mean, the 1, I mean, this one in the second column. So I will consider that one in the second column, first row, in a moment. But for a moment, I will just focus on the entries below the main diagonal. Okay. So when I look at this 1, and below that 1 in the main diagonal, you have zeros. So I consider the next row, next column. So I consider this 2 in the third row, third column. Okay. And actually the numbers in the third row are all the even numbers. So let me multiply 1/2 to the third row. Then we get 1, 1, 1, 2, 0, 0, 1, 2, 1, 1, 0, 0, 1, 0, 2, 0, 0, 1, 0, 2. So even though I have so many non-zero values above the diagonal entry, let me focus on this one below the diagonal. I want to eliminate that 1 to 0. So what I can do is you can multiply -1 to the third row, then you get 0, 0, -1, 0, -2. And if you add these numbers to the fourth row entries, then 1, 1, 1, 2, 0, 0, 1, 2, 1, 1, 0, 0, 1, 0, 2, and 0, 0, 0, 0, 0. Okay. And then at this point, using this 1, I want to eliminate 1 and 2 above that 1 to 0. I mean, I want to multiply negative 1 to the third row entries, then you get negative 0, 0, negative 1, 0, negative 2. If you add those numbers to the first row, then you get 1, 1, 0, 2, negative 2. And then if I multiply negative 2 to the third row, you get 0, 0, negative 2, 0, negative 4. If you add those numbers to the second row, you get 0, 1, 0, 1, 0, and 1, negative 3. Am I correct? Um, oh, just a second. Something. Oh, yeah. So if I 0, 2, negative 2, 0, 0, 1, 1, yeah, minus is negative 3, 0, 0, 1, 0, 2, and 0, 0, 0, 0, 0. And then using this, if I multiply negative 1 to the second row entries, then you get 0, 0, 0, 0, just a second, 0, negative 1, 0, negative 1, plus the 3. So if you add them, you get 1, 0, 0, 1, 1, 0, 1, 0, 1, negative 3, 0, 0, 1, 0, 2, 0, 0, 0, 0, 0 is obtained. Now, if I perform the column operation, when I multiply negative 1 to the first column and then add it to the fourth column, this 1 will become 0. When I multiply the negative 1 to the first column and then add it to the fifth column, this 1 will become 0 as well. Similarly, if I consider the column operation using the second column, these 1 and negative 3 will become zeros. And then if I consider this scaling operation, column operation with the third one, I can change this 2 to 0. So by performing many column operations, you get this. Okay. So what did I do? So given this matrix, 5 by 4 matrix, I just considered introduce the non-zero value in the first row, first column. Initially, I didn't have the non-zero value. I had 0. So I performed some row operation. Interchange operation was considered and to get non-zero value. And then I made all the entries below that number to 0. Right? So that was the first step. Then you consider this entry and then you put 1 there, and using that number I could change all the numbers below the number to 0, and I didn't care about this. So the above that number I didn't care, but I do care the entries below that number. And then I consider the third column. So I have some non-zero value with zeros. I have another non-zero value with zeros. And then you get non-zero value there, and then you introduce the zero. So that was the step. And then what did I do? So at this point, you may have some values here. And then I cleared the entries above those numbers. So from here, I have ones and zeros. And I have below the number one, I have zeros. I have something like this. And I don't care about these yet. And I have zeros here. Okay. So this is the shape. And then I go to 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. So actually I introduced, so I have this shape. So I first considered this corner, then, oops. So I introduced the zeros here in the first column. Then I considered these zeros, and then I considered this zero. So I go down this way, then the second column, then the third column. So I go this direction first, right? That was the first step. Then what did I do? I didn't consider these fourth and fifth columns yet, but I considered, I introduced the zeros here. And then I go this direction, this column. So I considered the third column first, and then I considered the first column. Previously, I considered the first column, then second column, then the third column. But now, when I change the values, I cleared from the third column, then second column, then first column. So I considered this direction. So that is the second stage. Okay. And then what is the third step? So up to this, I performed row operation. And then I performed many column operations. To change these values to zeros. Okay. So so at that point we introduced many zeros here. Okay. So so that is the third step. So that is the how I derived the matrix from a matrix. So please follow the order I'm using. Okay. So that's the first observation. So that's how I derive D from A. Now, now the second thing you need to observe is this. In D matrix, D consists of many zeros, right? So D consists of many zeros. It has only three non-zero values in the first row, second row, third row, right? So that those three ones will show that the rank of D is 3. The theorem claims that since the D, please note that even though I'm using arrow, okay, please note that D can be written as a product of A with many elementary matrices from the left or from the right, right? And elementary matrices are all invertible and they preserve the rank, right? So the rank is not changed before or after you multiply some invertible matrix. That's why the rank of A is 3. Okay? So the theorem says, the theorem, so the theorem we just considered claims that the rank of A is 3, meaning, which means A has 3 independent columns. That is okay. So that is the claim. Okay. Anyway, let's call it a day here, and thank you for listening. And see you on Tuesday. Please come to the classroom. You need to come physically. Okay, in person. Okay. Anyway, thank you for listening, and see you next week.